Alright, let's hit it. Today we're talking about the second of the deflection methods, and it will be called the moment area theorem. This theorem really stems from the fact that in reality beams have a lot of different loading and boundary conditions as well as sectional properties. And so the double integration method is not the most convenient of methods for handling varying properties in beams. And to begin with, I'd like to state a number of standards when it comes to moment area theorem. Anytime I have a beam that's concaving upwards, kind of like that, then I'm dealing with positive moments. So M is positive. And anytime my beam is concaving downwards, then I'm dealing with negative moments. And so I could give you a beam, perhaps simply supported, and this beam can have any arbitrary loading on it. And the corresponding deflection due to the externally applied loads can have any arbitrary shape, kind of like that. What the moment area theorem does is to cut the section, or to cut the beam at two sections. One will be called section A, so we call this A, and the second will be section B. And what it really does is to compare the slopes and deflections between these 2 points. And so if I were interested in slopes between B and A, I would write theta B slash A, which means slope at B relative to A. And that would equal to the area underneath the curvature diagram, curvature being M over EI. This was something we discussed in the last lecture, dx. And we don't really need to integrate, we just have to find the sum of the areas underneath that curve, which are usually rectangular, or they are trapezoids, and they're very easy to calculate. And so theorem 1 of this moment area algorithm is that the change in slope between any 2 points on the elastic curve is equal to the area of the curvature diagram between these 2 points. And that's something important to keep in mind. So let's do an example involving slopes. Suppose I have a cantilever, and my cantilever has a length of L and properties of EI. My cantilever, and there's a point load at the very far end of magnitude P, and I have properties EI and a length L. So if I were to obtain my moment diagram, it would look like this. So the first one is going to be my moment diagram, and the second diagram will be my curvature diagram. So the first is mx, and the second is theta x. And with the first one, what I have is minus PL, and some minus there. And I will also have my curvature diagram, which is my bending moment diagram divided by the sectional properties minus PL divided by EI. So that's what I have. And if I were interested in the deflected shape of my beam, it would look somewhat like this. Concaving downwards. And the question that is being asked of me is, what is the slope at this point here? So I'll have point A and B, and I'm interested in knowing the slope at point B. I know for a fact that the slope at point A is going to be flat and it's going to be 0 due to the fixed end nature of the support at reaction A. So what I can do is to simply write theta B slash A is equal to theta B minus theta A. I know theta A is equal to 0, so we'll call that 0. And what I'll end up with is integral B to A mx divided by EI dx. And what I need to do is to calculate the area of my curvature diagram. So I need to find out what this whole area is, and I'll have integral BA minus PL EI dx, and that area is really straightforward. It's this length is L. We just calculate the area of the triangle, and we should end up with minus 1/2 PL squared divided by EI. And that's really it. We have found the slope at the very tip of our cantilever due to a point load being applied at the free end. The second component of the moment area theorem has to do with deflections, and that's what we're going to look at next. And it really says that if I have a beam, in this case again a simply supported one, and I have any arbitrary deflections underneath this beam, I'm going to be dealing with two sections again. Section A and section B. And the vertical deflection, based on the second theorem, the vertical deflection of the tangent at A with reference to tangent at B is equal to, so that's T A slash B is equal to X bar. I'll explain in a minute what that means. BA M over EI. And what X bar really means is it is the centroid of the area between A and B. So whatever the centroid is, it could be anywhere here. So let's write that down. X bar is the centroid of the area between A and B. Let's look at another example that demonstrates the second component of the moment area theorem. And this new example will again be another cantilever. And cantilevers are kind of easy to work with and easy to imagine in terms of how they deflect and whatnot. And with this new cantilever, I have to draw 3 lines, one for bending moments and one for curvature. And here is my fixed end. I have a reaction or a force of 4 kilonewtons being applied, and I'm measuring X from here, from the left hand side, and the length of my beam is 3 meters, and the elastic modulus is 2 times 10 to the power 5 megapascals, and that's what this E means, is 10 to the power 5, and I is 4 times 10 to the power 6 millimeters to the power 4. And the first thing I need to do is to figure out what my bending moment looks like. And again, because we're dealing with point loads, our bending moments are going to be triangular in nature, somewhat like that. And if I'm drawing the BMD here, we'll have a magnitude minus 12. Because it's concaving downwards, it will be negative. And our curvature diagram will be the same thing divided by EI, minus 12 EI. And the units here are, by the way, kilonewton meter. And so the first thing I want to do is to find out what X bar is. And X bar is the centroid between points B and A, which reminds me, I have to state what A and B are. That's B. That's what we're interested in. And with this example, we're interested in the deflection at point B. And so what we're going to do is state what the centroid is. It is 3 2/3 is equal to 2 meters. And centroid is, in this example, is measured to B, from B, because we're interested in point B when it comes to the deflection. And so the next thing we're going to do is TB relative to A. So we're interested in the difference in height between the tangent of B and tangent of A. We know that tangent of A is flat because point A is fixed end point, and it's going to have a 0 slope scenario. And what we end up with is that is the area of the triangle here, this area here, times X bar. And that'll get us to minus 36 over EI. The units for which will be kilonewton meter cubed. And because the tangent at A is equal to 0, I can simply state that delta B, that is the deflection at B, is equal to minus 36. I have to do a number of unit conversions here. These include going from kilonewtons to newtons, and going from meters to millimeters. And these are my sectional properties, the moment of inertia and the elastic modulus. Something I forgot to do is to keep a consistency when it comes to writing these E's. Here we're referring to 10 to the power, so 2e5. And here we go. And lastly, we calculate this sum, and we should end up with minus 45 millimeters. All right. So now that we're familiar with the two theories that constitute the moment area theorem, we can now do a tougher example. And this tougher example will have several steps, and we have to really think deep and recognize all these relationships, all these geometric relationships that exist between the different components of our slopes and deflections and tangents. So we're given a beam that is fixed at one end. It has a hinge here at this point, and there is a roller support here. And there's a point load applied that has a magnitude of 60 kips. And the lengths I have are 10 feet, 10 feet, and 20 feet. And the question that is being asked of me is, suppose I have these points A, B, C, and D. Find the rotation at the location of C, and also find the deflection at the location of C. So the weird thing, anytime you have a hinge, is that the right side and the left side of the hinge won't have the same rotations. And that's not very intuitive for our imagination, because this is one of those conditions where we have a kink in the beam. We call this a kink. And this is very rare in real life. So it's not one of those conditions I expect a lot of people will encounter. And so if I were to draw the deflected shape of this beam to sort of imagine it better, especially now that we have to calculate these properties, what I need to do is to first draw my boundary conditions, the fixed end and the slider, and to really include the location of my hinge somewhere here. And so my beam's going to deflect downwards, kind of like that. And this will have my hinge, and it will go back up, kind of like that. Here we go. And this is the location of the applied force, P. If I were to label my locations of interest, I have A, B, C, and D. One thing I like to highlight is that C is not necessarily the lowest point. So delta C is not necessarily delta max. This makes things kind of harder to calculate. Alright, so what I'll do is to go through the steps that are necessary to calculate the deflection and rotations at point C. So let's write down the steps. The first thing I need to do is to find my BMD, that is my bending moment diagram, and my deflected shape. So this is kind of my deflected shape. So what I like to find out is my BMD and delta. The second thing that I need to do is to look at the left side of my beam. I have fixed end, and I have this kind of deflection, as we noted in the deflection diagram right above. So the first thing I need to do is to find out what delta BA is going to equal. Delta BA. And this is really straightforward because the left side of this beam is flat and the right side is not. And so finding the relative deflections between the tangents will be really straightforward. For point 3, or step 3, what I need to do is to find delta BD. And that really means drawing the, looking at the right side of the beam and thinking about how the deflection is going to be. In this case, it's going to look somewhat like that. Going back up. And if I were to draw a tangent from point D to point B, it would look somewhat like that. Somewhat like that. And delta BD is this vertical height between the tangent of B to the actual, or the point of tangent of B. So this is tangent from D, and this is another tangent that's going from B. And this would be delta BD. You could also think about this as TBD. These are the same things. Okay? Something that I figured out from step 2 is the simple fact that this height here is in fact delta BA. So now I know delta BD, and now I know delta BA. If I were to add these two together, if I were to do delta BA plus delta BD and divide these two by 30, which is this length here, I would have a rotation theta D. So now I would find out what theta D is equal to. And we call this step 4. So let's remind ourselves, what are we interested in? We're interested in finding out the location C, what the rotations and deflections are. That's what we're getting into. And it's going to be a slow process because this is kind of a hard example. But if you can understand and comprehend an example like this, you can pretty much solve any kind of moment area theorem example. The next thing I can do is to find out delta CD. And for delta CD, I'm going to look at the right side of my beam, and I'm going to look at its deflection. It's going to look like that. And this is kind of point C. Then that's D. And when I draw the tangent from D to C, this is going to equal to delta CD. And this is the actual delta C that I'm interested in, and that's where we're going to get to. And again, something to remind you is that the location C is not flat. It could have any arbitrary slope. People tend to think that the location of the point load will be the maximum deflection and the point of zero slope. That is not true. Let's keep that in mind. And so what I'll have is, from triangular equalities, I can say 20, this length here is 20, and this length up here is 30. 20 divided by 30, I have delta B prime. By the way, this thing here is equal to delta B prime. Delta B prime minus delta CD. And that easily we can find out what the location of delta C is. And lastly, what I can do is to simply solve for theta C. And now that we know what theta D is equal to, solving for theta C will be really simple. So my deflected shape will look somewhat like this. And this is the location of C. If I were to draw a tangent from C all the way to D, that's D. And if I were to draw a tangent from D all the way to C, this angle here is equal to theta CD. And if I know what D is, then theta C is going to equal to theta CD minus theta D. Because anytime I have two lines crossing each other, the sum of the angles between those two lines is equal to the actual angles of these two lines. So this is theta D here, and this is theta C here, and the cumulative sum of these two will amount to theta CD. And using the information that we have from earlier, theta D and theta CD, I can easily find out what theta C is. Okay, so if you can really understand and comprehend and grasp the concepts that we have discussed in this third example, then you can go on and solve any kind of momentary theorem type question and really master the art of calculating deflections in beams. I hope this has been a useful session for you. Leave any comments or feedbacks, and I'll see you in the next lecture.